Alright, let's do the second half of the page for calculations of heats of reaction. Number 3. Calculate the standard change in enthalpy for the equation 2a plus 6d is 4b plus g using this list of equations. Alright, this is a demonstration of Hess's law, and what I'm going to do to solve is I'm going to first list out the main base equation that we want to target. The equation is 2a plus 6d and an arrow, which separates the product and reactants inside, 4b plus g. Oh, it's covered up. Yep, this is the equation. This equation right here. And we're going to use the following equations to solve for it. We're going to have 2. G is going to be 2a, and the enthalpy is going to be 40. Enthalpy is going to be 42 kilojoules. And we have the third equation, which is 3b, arrow 2b, and then we have delta H equals 25 kilojoules. Alright, and we're looking for the delta H of this first base equation. What we want to do to solve this is we want to look at our two given equations in red, and we want to compare this to the main equation. And you want to basically balance it using this. Alright, so when we look here, we have G here on the product side, or the reactant side. And in our blue equation, the main equation, the G is on the product side. That means we have to move this equation around. We have to flip number 2 in order to have the G, in order to have this G go to the product side. So I'm going to write it out. The second equation, 2, and I'm going to do a flip 2a and an arrow G. And then since we flipped the equation, our delta H is going to turn negative. So we started with a positive 42. Now we're going to end with a negative 42. Alright, and we're going to take a look at number 3. So we have 3D on the left and 2B on the right. Oh wait, but the D on the blue equation, the main equation, has a 6 to it. But this equation only has a 3. That means we have to multiply our third equation by 2. So we have the third equation, bring it down. So it's going to be 2 times 3 is 6d, and an arrow, and since you did it to the reactant side, you also have to do it to the product side. So 2 times 2 is 4b. And since we multiplied everything by 2 on our equation, we have to multiply our enthalpy by 2. So 2 times 25 will give you 50 kilojoules, and this is negative 42 kilojoules. Alright, now we can compare with our main equation. So our main equation is 2a plus 6d, arrow 6b plus g. So we can take a look at our equation now, and we can see that there's a 2a, check, 6d, check, 4b on the right, check, and g on the right of the arrow as well. And therefore, our equation is now complete. Now, how do you find this? When we verify this, we're going to write our equation. This is going to be our final equation. We're going to bring it down this way. And we're going to make sure all of these are going to equal the main equation up here. Okay? Let's bring it down. 2a plus 6d, arrow, and then we have a 4b here and a g here. 4b plus g. And we want to look and say to ourselves, is this number 4, is this equation identical to number 1? And yes, it is. So the delta H is calculated, and by add these variables together. And the only reason why we do this is because we have to make sure that these have correct signs and are the correct numbers in order to get the correct enthalpy for our base blue equation. So we're going to add negative 42 with 50, and you're going to get 8 kilojoules. So your delta H, your enthalpy, change in enthalpy for your equation 2a plus 6d turns into 4b plus g is going to be 8 kilojoules. Okay, so is our answer positive or negative? Right, it's positive. It is endothermic. Alright, let's try number 4. Number 4. What is the enthalpy change, delta H, in kilojoules for the following reaction? And it gives us a base equation to work with. Looking below, it says use the enthalpy changes for the combustion of aluminum and iron, and it gives us two of the equations that we need as bases. All right. So first thing we're going to do is we're going to write the first equation, the base equation, in the blue circle down. This is going to be our target equation, and this is what we want to reach. 2Al solid plus Fe2O3 in solid, and then the arrow separates our reactants and products. We have 2Fe in solid and Al2O3 is solid. Next, we got to write our other two equations near in the red brackets down. We have 2Al solid and 3/2 oxygen gas, and then that combines into Al2O3 solid. And our third equation says 2Fe solid, let's make the S a little better, solid, plus 3/2 O2 in gas form is going to make Fe2O3 in solid form. And our delta H for our first one is going to be negative 1676 kilojoules, and our second one is going to be negative 822.1 kilojoules. Alright, so first what we want to do is we want to make sure that we have all the equations written correctly, of course, and then we want to look at our blue equation, the base equation, and see what we can do to the red ones, the two of the red ones, number 2 and number 3, to make it into the blue one. So we can take a look at number 2 first. Let's take a look at this one first. We have 2Al on the left, 2Al on the left, and Al2O3 on the right of the arrows. Alright. And because the equation does not have a 3/2 O2, nor any O2s for that matter in the blue equation, we know that's going to somehow cancel out in the process of us balancing this out. That means for now, we're going to leave 2, untouched 2, and we're going to move on to number 3. Number 3, we can look at 2Fe solid, but the Fe solid on our red equation on the left side of the arrow, and on the blue equation, what we want to get, it's on the right, right? And it is the same thing. 2Fe solid form is the same thing. So what we're going to do is we're going to multiply, or we're going to switch. We're going to switch to the sides of all of this. Move all the reactants to the product side, and move the product to the reactant side. All right, let's write number 3. We have Fe2O3 solid, and then the arrow goes back, and we have 2Fe solid plus 3/2 oxygen gas. And our delta H, we flipped our equation, so the delta H is going to flip signs. So it's going to be positive 822.1 kilojoules. Now we can take a look at our base equation again and see if we can cancel these out. All right. And so what we did here was we got this, canceled this part, and made it into this. So we're going to say converted. And we can ignore this one for now. Okay, now let's take a look. We have Fe2O3 on the left-hand side of the arrow, Fe2O3 on the left-hand side of the arrow, that's check. On the right-hand side, we have Fe, 2Fe, we have a 2Fe here, check. We have a 3/2 O2 on the right-hand side, but at the same time, we have a 3/2 on the left-hand side as well. So we can go ahead and cancel that out. That is non-existent anymore. All right. Then we take a look at our number 2 equation, the one we didn't touch yet. We can look at 2Al. 2Al is on the left-hand side, both the same location of the arrow. And we can look at Al2O3. Al2O3 is on the right-hand side of the arrow, just like the blue equation. Therefore, this one is also good. And this is going to be our final equation. We can write this final equation again. We have 2Al solid plus Fe2O3 solid, and then the arrow, and then we have 2Fe solid, 2Fe solid plus Al2O3 solid. That is the identical form of this identical form of the original given equation, so we are all set. To calculate delta H, we did what we did on the previous question, and we can go ahead and add these two values up. We're going to add the delta H value of this one, and we're going to add the delta H value of this one together. And then when you add negative 1676 and take negative 1676 and add 822.1, you are going to get your final answer of negative 853.9 kilojoules. That is your final answer. And since we have a negative here, we have a negative on the front, that means our answer is going to be exothermic. We are releasing heat, exothermic. And that's it.